Okay, continuing in section 4.2, now let's put all the terms together and the theorems together that we've just discussed. And they culminate in theorem 3, which is on page 203 in your text, extrema on a closed interval. And we also are relying on one theorem, theorem 1 in this section, which I did not post or include on this sheet, but you have it in your text so you can look it up. If you assume that a function is continuous, assume that f is a continuous function on an interval a to b, and let f of c be an extreme value, so maybe it's a local max or a local min. Then see that input that gave you that extreme output is either a critical point or it's one of the endpoints of the interval, a or b. How do we use this theorem? This theorem is a culmination of all the definitions and the theorems that came before it, and here's how we might use it. If we're given a function and a closed interval, that is with the bracketed endpoints, if we're given a function and a closed interval and we're asked to find the extrema, the previous theorem says, well, if you've got an extreme value, then it's either occurring at the x value that's a critical point or one of the endpoints. So, how do you find the critical points? Got to remember the definition of critical point. A critical point is a place where the derivative is either 0 or it doesn't exist. All right, even though we weren't told explicitly to do it, we need the derivative. So let's find the derivative, f prime of x, using the power rule, because this is just a polynomial. We get 6x squared minus 30x plus 24. And that is, I'm going to factor a 6 out to make it a little easier on myself. And now I can see that the two linear factors that make this polynomial are x minus 1 and x minus 4. I believe that'll do it. And just a quick double check, there's a negative x and a negative 4x, which gives me this, and the product of these two is positive 4. So where is f prime 0? And in factored form, and we've been talking about this in the past few weeks, when we have our derivative in factored form, it's really easy to see where it's equal to 0. That happens at x equals 1 and x equals 4. Okay, always go back and remember, what are we doing here? We're trying to find the extreme values of this function on the interval from 0 to 6. And we're told in the previous theorem, extreme values will occur at critical points or at one of the endpoints. So we need to see how high is the function at, or low is the function at x equals 0, at x equals 6, those are the endpoints, at x equals 1 or x equals 4, those are the critical values. We also should give a nod that we've checked the hypotheses of the theorem. F is a continuous function on the closed interval 0 to 6, and it is. F is polynomial, they're continuous everywhere. So let's check at x equal to, I like to put them in order, x equals 0, x equals 1, x equals 4, and x equals 6. F of 0, easy to compute, is 7. F of 1, also fairly easy to compute, is 18. F of 4, I had to use a calculator for, and I get negative 9 there. F of 6 is 43. These are my values, or the outputs. These are my inputs. So these are the C that we're checking, the various x values that we're checking. And so now what you're looking for is, you don't have to even have the graph of this function. You're just looking for the output that is highest, that's this guy, and the output that is lowest, that's the negative 9. So the absolute minimum value on 0, 6, that closed interval, is negative 9. That's the value. And the absolute maximum value on the interval from 0 to 6 is, it happens when we plug in x equals 6 and out comes 43. That's the output. This is the value. And I keep emphasizing that we call that the value. It's the output of the function. where it occurs is the input of the function. Okay, and then to find the extrema for this function on the interval from 1 to 4, we're again going to need the derivative. Which I'll rewrite by getting a common denominator is 2x squared minus 8 over x. And that is 2 times x squared minus 4 over x. The critical numbers, critical points, are where this derivative is not defined or where this derivative is 0. One more factorization gives us a complete factorization of that derivative. I can see the derivative is 0 at 2 and at negative 2. And I can see that the derivative is not defined at 0. However, technically x equals 0 is not a critical number because it's not in the domain of the function. I can't plug x equals 0 in this function because natural log of 0 is not defined. So the only critical numbers are x equals plus and minus 2, and only 2 is in the interval from 1 to 4. Check f at 1, 2, and 4 to find the extrema. You finish, you try.